Hey everyone, welcome back. So today in this video, what we're going to talk about is something called electric potential difference, also called simply just electric potential or potential difference, or it's got a few other names, some of which we'll get to a little bit later. All right, but to do that, in order to get to this concept of this electrical potential difference or whatever you end up calling it, got to get a little kind of background, some filler almost. Right? So first, we need to start with this idea of electric field, okay, which hopefully you've had a chance to take a look at. Okay, so let's take this positive charge and the electric field lines emanating from that charge. Okay, now I'm actually going to draw a few more lines just to kind of get my point across here for what's coming up next. So I'm going to actually triple the total, or maybe not triple, I'm going to actually get a few more than that in there. Anyway, I'm just adding a bunch more lines. Okay, so as you can see, I've added quite a few more lines. Now, let's take this particular example to start. Let's take a look right here. Okay, this chunk of 3 lines right here, really close to the charge. Okay, with a circle of about, or I guess an oval of about, I don't know, 1.5 inches maybe of on this long axis. I fit 3 lines in here. Now, what I'm going to do is I'm going to take this same size circle or same size oval, okay, and I'm going to see how many lines do I now kind of hold within that circle, right? So I've just expanded these lines just to kind of make my point, and you can see that, I even draw this a little bit bigger, I'm only holding now 1 line within that chunk, that area. Right? So what this tells you is that an electric field like this from a single particle or even a series of 2 particles, your electric field is not uniform throughout all of space. Okay, so the further and further away you get from that electric field, the weaker and weaker and weaker that electric field is. Right? Think about it like with your electrostatic force equation, right? It's F equals K, that electrostatic constant, times the product of the charges divided by the square of the distance between them. Or in other words, the further and further away you get from the 2 charges, you end up with a weaker force. Same idea with the electric field. Remember, it's E equals that force divided by Q. So the further and further away you get, the weaker and weaker it gets. Okay? Now, in order to kind of proceed, what we need to do is look specifically at uniform electric fields, which means that no matter where you are in that electric field, the strength of that electric field is the same, is constant throughout all of space. Okay, so let's do this. I'm going to draw an image. So what I've got here are 2 parallel conducting plates, right? So it's made of some sort of metal. And I'm going to put a charge on each plate. Okay, so I'll make, just for the ease of our picture, so to make it a little bit more familiar with what I'm going to compare it to, we'll put the positive charges up here, and we'll put the negative charges down here. Okay. Now, if you remember from your rules of drawing electric field, we've got to make sure they're straight. We've got to make sure they touch the charged objects, in this case, the plates. We've got to make sure that they don't cross. We've got to make sure they have arrowheads, and we also have to remember that they go from positive to negative. So I'm going to draw 4 lines, because that's the other rule, how many lines you have. 1, 2, 3, 4. Okay, so here's my 4 electric field lines within this system here. We have these 2 oppositely charged parallel plates. All right, now, quick little aside, if we were to draw it just like this, we'd see that on the edges, you have these kind of curved lines. We're actually going to pretend, because that's what we do in physics, sometimes we take approximations, we're going to pretend that these plates are infinite, so there is none of that effect. So all of the lines that we're going to look at are these nice straight lines. Okay, and we're able to kind of calculate that here. Now, we can actually kind of compare this system to a gravitational field. Okay, think of down here as the ground, up here as the sky. Right? If I have something up here in the sky, which way is it going to go? It's going to go down. Okay, so that's kind of the analogy we're going to make here for a second. right, so let me draw a positive charge in here, right? Because that's going to follow that same line. Right? Remember, the electric field lines point in the direction of the way a positive charge would go. So here's my positive charge up here, furthest away from your negative plate. Right? So in other words, if this is my ground here, I've got this marker up here, right? It's up somewhere away from kind of where it wants to be. Now, what happens if I take this charge and move it along this line? Okay? I'm going to draw a dashed line so you kind of see what I'm talking about. Okay? So if I take my charge and I move it along this line here, okay, what's going to happen to the electric potential energy if I move it along this line? Well, let's think about it again with gravity. Okay, so here's my ground, here's my marker. Okay, if I move my marker along this plane, okay, my gravitational potential energy won't change, right? Because it's PE equals mgh. So if that h doesn't change, that potential energy does not change. Same idea here. Okay, if you move this charge along this dashed line, your electric potential energy will not change. Right? Cool. Now, if I were to let this charge go and it were to fall a little bit, okay, now I can move it across this line here. Okay, it's fallen a bit. So now, along this line, the gravitational potential energy doesn't change. But if we compare this line to this line, we say the electric potential energy, sorry, I meant to say electric before, that electric potential energy it changes, it decreases. Okay? If I were to draw, you a little bit closer, you'd see that it drops a little bit more, right? So as you go from here to down here, the electric potential energy will decrease as it moves through of this positive charge. Okay? Now, what does that mean? Well, honestly, it can mean a lot of things, right? If I'm looking at this electric field and I want to study this electric field, what I've got to do is kind of sort of take how much charge there is out of the equation. Okay? So I need to find a way to compare this electric field to another electric field, but not have it matter if I put a proton in here or if I put an alpha particle in the other one, where an alpha particle is a helium nucleus, which has a charge of 2 times a single proton. I need to be able to kind of figure that out. So we're going to work in this whole system a way to get that to happen. Now, first, what are each of these lines called? They have a name. They're called equipotential. My handwriting kind of messed up on that one, so let me rewrite it so you can read it a little bit better. I'll do this, draw a little arrow. They're equipotential lines. Okay, so again, along here, that's the same. Along here, that's the same. But if you change from here to here, you're changing how much energy there is. Okay, now, it's an interesting idea that we just talked about. Let me get my shirt. Okay, changing the energy. Okay, if you have this electric field and you change an energy, or if you change the energy of any object, what's that called? Well, that's work. Remember, work is a change in energy. Just in this case, it happens to be a change in electric energy. So I'm going to actually write that down. I'm going to say we have our work here. Okay, now, again, we want to take charge out of this equation for work, or this energy, right? Because again, work, energy, similar kind of ideas. So what I'm going to do is I'm going to divide this work by Q, the charge. Okay. And if I set that equal to this symbol V, that is our equation for electric potential difference. Let me write that down. Electric okay. So that work is that change in electric potential energy, that difference. But dividing charge from that work changes it from electric potential energy to just this idea of electric potential. Okay? So it's V, capital V, equals work divided by charge. All right, now let's talk about units, right? You need units in physics, otherwise you don't know what you're talking about. So, what are the units for work? Well, the units for work is the joule. What's the unit for charge? That's a coulomb. So you could say that the electric potential difference, which is work over charge, has the units of a joule per coulomb. But believe it or not, this has a name, which is probably familiar to most of you. That is called the volt. Right? Now, in problems, you can symbolize the volt with also the capital letter V, which means that electric potential difference has the same symbol for its equation and its unit. But what that also means is the electric potential difference is also known as voltage. Voltage, right? I'm sure you've heard of voltage regarding electricity. Oh, this thing's got 10,000 volts. Oh, it's 120 volts, or it's your car battery runs on 12 volts. It's a 9-volt battery, right? That's your electric potential difference. And essentially what it does is it acts as a pressure, sort of. It's kind of an analogy many people make, to push the charge through the electric field. Right? So when you say you have a voltage of some magnitude, what you're saying is that you've got some amount of pressure acting on that charge to push it through the electric field, right? The electric field produces the force. Now, when you compare one spot on an electric field to another spot on the electric field, right, you're changing your energy. By changing your energy, you're doing work. And if you kind of sort of remove this idea of how much charge that work is being done on, because you want to look at it, if it doesn't matter if it's a proton or some other charge, then you have this electric potential difference. And that's what it is, right? Bottom line, this is what you've got to be able to understand. That your voltage, your electric potential difference, is your work per charge. How much work is being done on the charge divided by the actual magnitude of that charge. Okay? That's all there really is to it. See you next time.